You know, it might sound a little strange, but every single material has a story, a secret biography, if you will, that tells us exactly how it's going to behave under pressure, from the first tiny stretch all the way to the moment it breaks. Today, we're going to become material detectives and uncover what that story really says. And this is what happens when a material's story ends badly. I mean, look at this. A concrete column, something that was meant to hold up an entire building, just shattered by the force of an earthquake. It's a stark reminder that the consequences of not knowing a material's limits are, well, catastrophic. So that just begs the question, doesn't it? How do engineers actually figure this stuff out? How on earth do they predict this kind of failure before it happens to make sure our bridges, our buildings, all of it stay standing? Well, the answer is actually pretty cool. You basically put the material itself on trial. And that brings us to the first part of our investigation, one of the most fundamental experiments in all of material science, the tension test. It's called a tension test. And don't let the simple name fool you. This is an incredibly powerful procedure that literally forces a material to reveal its innermost secrets. The whole process is super methodical. First, you create a standard-sized sample of the material. We call that a specimen. Then, you lock it into a machine that just slowly, but with incredible force, pulls it apart. And all the while, the machine is recording two absolutely critical pieces of data: the force it's applying and exactly how much that specimen is stretching. Now, to measure that stretch with amazing precision, engineers use this clever little device called a strain gauge. You can see it right there, that small patch that's basically glued to the specimen. It's a tiny, super sensitive electrical circuit that actually deforms right along with the metal, letting us measure changes in length that are way too small for the human eye to ever see. Okay, so we have all this data, the force, the stretching, but what do we do with it? Well, this is where the magic really happens. All of that raw data gets turned into something truly special. It becomes the material's biography. It's called a stress-strain diagram. Now, I know stress and strain can sound a bit technical, but the idea is actually pretty simple. On the vertical axis, you've got stress, which is basically just the force being applied over the material's area. Just think of it like internal pressure. And on the horizontal axis is strain, which is just a fancy way of saying how much the material has stretched compared to its original length. This one single graph tells us everything. And this is exactly why it's so powerful. This isn't just a bunch of data points. It's the complete, unabridged story of a material, from the very first bit of stretch to its final catastrophic breaking point. Every single twist and turn on this curve is a chapter in its life. So, what do you say we read that story? We can break down the journey of what we call a ductile material, like steel, into 4 really distinct chapters. Chapter 1, the elastic region. This first part, the straight line, is where the material acts like a perfect rubber band. You can pull on it, it'll stretch. But if you let go, boing, it snaps right back to its original shape, completely unharmed. This is its happy place. This is where materials live their everyday, working lives. But if you keep pushing the stress past that region, you hit Chapter 2, yielding. This is the point of no return. Once you cross this line, the material starts to deform permanently. Even if you remove the force right now, it would never go back to its original shape. It's been forever changed. And this brings us to a really fascinating third chapter, strain hardening. Now, you might think that after being permanently damaged, the material would be weaker, right? But it's the total opposite. Its internal structure actually realigns and it gets stronger, able to handle even more stress. It climbs all the way to a peak called the ultimate stress. That's the absolute maximum load it can ever possibly bear. But of course, nothing lasts forever. After hitting that peak strength, we get to Chapter 4, necking. A single weak spot in the specimen begins to thin out, almost like you're pulling a piece of taffy. This is called necking, and from this moment on, the end is near. The force needed to keep stretching it actually starts to drop, because all the damage is now focused on this one little spot. And here, you can see what that graph is actually showing us in the real world. That physical neck is forming right there in the middle of the specimen. That abstract dipping curve on the diagram corresponds directly to this very real, very visible change in the material. And then finally, the break, the end of the story. And for a ductile material like steel, it leaves behind this really characteristic signature, what we call a cup and cone fracture. It is the very last page of its biography. Now, here's the thing. Not all materials write the same story. They tend to have very different personalities, which usually fall into two main categories. So on one side, you've got ductile materials, like the steel we just saw. They stretch, they neck, they basically give you tons of visible warning before they fail. They're also amazing at absorbing shock and energy. On the other side, you have brittle materials, like that concrete column from the beginning. They show very little deformation. They just take the stress, and then all of a sudden they just snap. No warning at all. So the really crucial point is, how much warning do you get? Well, for something like mild steel, that number is 38%. That's its percent elongation. And think about what that means. It means that by the time it finally fractures, it has stretched by over a third of its original length. That is a massive amount of deformation, a huge blinking red flag that failure is on its way. So we've put a material on trial, we've read its biography, and we've understood its personality. But why does any of this actually matter? Okay, let's bring it all back to the real world. It matters because engineers read this story to make literal life or death decisions. They choose ductile materials for critical structures because they give you a warning. Understanding these curves lets them design everything with a huge built-in margin of safety, making sure that the normal loads in a bridge or a building never even come close to the material's breaking point. This knowledge, this simple curve, is what stands between a safe structure and a pile of rubble. Which really just leaves us with one final thought. After reading these secret biographies and seeing the huge difference between a long, drawn-out failure and a sudden brittle snap, what kind of material would you want holding up your world?